Design and fabrication of solar panel with sun position tracker. Rationale or objectives. Design and fabrication of solar panel with sun position tracker. Design and fabrication of solar panel with sun position tracker. To develop a new solar panel design with better energy harvesting efficiency with the capability of tracking the position of the sun using real-time tracker. Daylight can be utilized as another form of energy by completely harvesting the light rays from the sun into a reliable, sustainable source of energy. Materials and methods. The SPT system body frame consists of stainless steel bar and iron rods. The overall height of the proposed system is 960 millimeters, whereas the system has a wide view dimension of 440 by 586 millimeters. Three rods, or also known as solar rods, are inserted with a small bearing through stainless steel or SS bar, which the rods are connected to solar panels and solar concentrator. Next, three servo motors are mounted on the SS at one end of each solar rod. These servo motors are connected by servo horns for a better grip. The motors helps to rotate the solar panels and concentrator in horizontal axis according to specific time interval. In the proposed system, a single SS bar is used to support all three solar panels with solar concentrators. The rotational movement.
The system keeps track of real time by using the microcontroller to acquire data using a real-time digital clock. The microcontroller then sends control signal to the servo motors in order to rotate the PV panels at the right angle and time interval. The middle panel is kept still and facing upward up until the sun reaches the zenith. Once the sun passes through the west, the stainless steel bar that holds the three PV modules begin to turn to prevent any shading from happening to the bottom panel. In simpler terms, before noon, the top PV panel is at the right and the bottom one at the left, while in the afternoon, the top PV panel is at the left and the bottom one at the right. When sunset comes, the PV panels will reset to their original positions, ready to be used for the. The experiment was conducted for 3 days, from January 14 to 16, year 2019, and collected data for 10 hours, from 8 a.m. to 6 p.m. This was due to Malaysia, the country where the study was conducted, received about 10 hours of sunlight at average. The inter-panel separation distance was set to 1.5 times the width of the panel to maximize the solar exposure of every panel. The experiment was done in an open space for the same reason. During the start of every day, the boards were all in their default mode where the top panel is at the right side. At 8 a.m., the panel faces at a 60-degree angle to the east where the sun rises. After 2 hours, the microcontroller received a signal after checking the real-time clock and turned 30 degrees upward. At 12 p.m., the motor rotates 30 degrees upward again. At 2 p.m., the stainless steel bar flips to the west, effectively changing the system to its afternoon mode. By the end of the day at 6 p.m., the system goes back to its original position. To see if the proposed system is effective, a photovoltaic panel with the same specifications was installed at a fixed position facing 15 degrees south directly towards the sunlight's path. Data was manually collected every 30 minutes for both the sun position tracker model and the static photovoltaic panel. A 7.2 ampere-hour and 18-volt lead-acid battery was used as the load for the system. To prevent reverse electrical flow, a 5-volt 1.2 amps pulse width modulation solar charge controller was installed in a series connection with each panel. This diagram explains the circuit of configuration of the sun position tracker model. A real-time clock is connected to the microcontroller where it controls the rotations of two things. First, the three individual photovoltaic panels via their servo motors which then produces electricity. Second, the stainless steel bar that hosts the three photovoltaic panels. When the microcontroller sends a relay, the stack then glides and changes its modes to default or the afternoon mode. The data logger in the diagram was added by the researchers to track their findings during the execution of their study.
Results and findings. The experiments were carried out for 3 consecutive days, which are 14, 15, and 16th of January 2019. It can be seen that the output power generally increases for all the cases from 8 a.m., reaching its maximum values at around the midday time, and then the produced power generally decreases, reaching its minimum values at around 6 p.m. As we can see, it is the sunlight that affects the power generated because the sunlight is the source of the energy. This could be mainly attributed to the increase of solar irradiance with the rise of the sun from early morning to the midday time. However, when the sun moves from midday time towards the sunset time, the solar irradiance continuously decreases, reaching the lowest level at around 6 p.m. The sunlight really impacts the power output that is generated. However, when the sun moves from the midday time toward the sunset time, the solar irradiance continuously decreases, reaching the lowest level at around 6 p.m. Consequently, the produced electrical power reduces correspondingly. In general, the PV system performance is significantly improved when the SPT system was implemented. The overall increasement is about 28.5% for all the working hours over 3 days testing time. This could be attributed to the two main reasons. Firstly, implementing the SPT system to the static PV system could certainly increase the solar irradiance penetration to the PV panels. The results were compared to evaluate the final performance of both PV systems. It is done with and without the SPT system. This was conducted by assuming there are three static solar panels to be compared with the three rotating solar panels in the SPT system. The results of the calculated cumulative energy of the SPT system are clearly greater than each of the static panels, even though the middle solar panel is idled for 2 hours. This superior performance of the SPT system is increased with the daytime reaching its greatest value at 6 p.m. This tells us that the SPT system excel better than the static panels. The maximum calculated cumulative energy output for the SPT system is approximately 280 watts, while the conventional system is 230 watts. This means that the performance of the PV system with the SPT system and solar concentrators is clearly performing better by about 21.24% than the conventional system, in addition to the aim of the SPT system. The proposed prototype of this work has achieved promising outputs. This was because of the PV system and the SPT system that harvested more solar energy than that of the conventional PV system. The work achieved its objectives, which firstly was studying the different working mechanisms of SPT models available in current technology. The work suggested prototype has produced an encouraging results. This was a result of the PV system and the SPT system harvesting more solar energy than the traditional PV system did. The study of the various SPT models, operating mechanisms that are currently available in technology was the first of the work's objectives, which are accomplished.
The biggest concern regarding this study was the lack of solar concentrator, the mirror at the side of the photovoltaic panels to the static photovoltaic panel where they made their comparison. the presence of the solar concentrator may have specifically boosted the efficiency of the sun position tracker model as it raises the solar exposure of the panels. A better approach would have been to also add a solar concentrator to the static panel or removing it altogether. The researchers also pointed out that it was possible that the surface temperature of the photovoltaic module may have affected the results. It would have also been better if they factored the cost of the batteries in order to run the system in comparing the cost to performance of the proposed system and the standard photovoltaic panels.